Okay. Hello, good evening to all of you. Welcome to this live session on the course that we have this semester on polymers. This is an introductory course which is intended to give you an overview of polymers as a subject. Because of this, we have a very wide range of topics that we will discuss in this course, and that's why the topic of the course is that we'll discuss the concepts, we will look at the properties of these polymers, and also where these polymers are used, the applications of these polymers, and then long-term usage, waste utilization, and recycling and sustainability of these polymeric systems. So I'm glad you have all joined. Good evening, as some of you are wishing me on the YouTube channel. Very welcome to this class. If there are any questions, please let them keep coming as they scroll. I will try to answer. So I can see that Shipra, Ashish, Dharmendra, Charan, they're all wishing. So good evening, all of you. And I hope you have started watching the videos and also started attempting the assignments. I also urge you to use the forum where Ask a Question is there so that we can have many fruitful discussions there also. And in fact, I have also posed a couple of questions. If you have seen those, one question I posed was on mucin. I don't know how many of you actually went and looked at what mucin is, an example of a biopolymer. And second question I posed was related to molar mass distribution. So it will be nice if you can participate in the forum during the course, and that way learning will be quite a bit more effective. And so today's session, Supratim is saying that there are a lot of queries. Yeah, welcome. Queries are welcome. We will also, what I'll also try to do is many of the queries, let's say if I'm going to discuss in the lecture itself, because we are just beginning, right? So there are so many more lectures every week that you will be watching. So if at all some of the queries that I can satisfy right now, I'll immediately answer. But there may be some queries, I'll tell you that, okay, wait, maybe in the 45th lecture or maybe 5th week or 7th week, we will discuss this. So yes, whatever queries you have, you can keep on typing. I'll take a look at the screen and try answering them. One of the things that I wanted to begin with was a question which was already asked, saying, what books can be used. And of course, polymer science is a very rich field. There is emphasis on synthesis. Chemical and electronic devices. So you have a very wide-ranging topics, and so there are lots of books. These three are the books that I find very useful. The book by Freud, Polymer Science and Technology, it's a very good introductory text, and it covers all the areas very well with good illustrations. Material Science and of Polymers for Engineers is again an excellent book with a strong focus on engineering, material properties, processing, rheology. It has very colorful illustrations, and so that is a very good book also. The Introduction to Polymers by Young and Lowell is a classic book, which again focuses a lot on synthesis and then basic characteristics of these polymers. So Durga Pawan has asked a question, will topics related to plastic packaging be covered? Yeah, there is one lecture specifically devoted to plastic packaging. But if you see, since this course is related to, concept and properties, so just because the polymer is used in packaging, and we will discuss all of packaging application in one lecture, but variety of properties because of which polymers are used in packaging will be used in several other lectures. What do I mean by this? For example, if a material is used for packaging, then it needs to be a very good barrier. For example, it should stop oxygen from going in, or it should stop carbon dioxide from going out in case of a PET bottle, where Coke or Pepsi or something is being packaged in a bottle, right? So there is a barrier property. It should stop light sometime. And the other thing it might have to do is it has to protect whatever is inside if it's a packaging material. So its impact properties have to be good. So not only we will discuss one lecture related to packaging materials themselves and packaging applications, we will have discussion related to impact properties of polymers, which is related to packaging applications. We will also have discussion related to diffusion, barrier properties, permeation, which is again related to packaging. So I hope that Durga Pawan answers that your question. Now Supratim is asking compatibilization and polydispersity index is related to polymerization process. What exactly is low cross-link density thermoset? So there are three questions. So I'll go one by one. Compatibilization is because we rarely use a single polymer. We will most often use a blend where we mix two polymers, or quite often we may have a composite where we put a glass fiber or a calcium carbonate filler or carbon fiber or Kevlar fiber in a polymer matrix. So therefore, given that now we are putting two materials in a mixture, interface can be the weakest link. So the material can fail at the interface. So therefore, it will be nice if we could make the materials interact with each other, the polymer and the filler, or one polymer and another polymer with each other. And this is what is called compatibilization. And so we, in fact, have a lecture on compatibilization, what is meant by compatibilization agents, which are the kinds of polymeric systems for which we have to use compatibilization. So we will discuss that in a separate lecture. In terms of polydispersity index, this is a measure of how wide the distribution is. So it's there in my lecture also. So basically, it's a ratio of weight average molar mass to number average molar mass. And so if you look at statistics, see, you can go and try to read about mean square versus mean itself. And so what happens is the ratio of these two tells you how broad the distribution is. And it's related, compatibilization is not necessarily related to polymerization process, but polydispersity index is related to polymerization process, because with polymerization, a polymer will result, and it's of interest to us to know what is the polydispersity of the polymer obtained with a given polymerization. And cross-link density is basically the chain or the polymer segment which is between two cross-link points. So cross-link polymers are network polymers where covalent bonding is there quite often. And between these covalent cross-link points, the chain is free. So what's the length of that chain? If it's a very high length of the chain, then that means the cross-link points are very few, which means cross-link density is less. So cross-link density gives you the number of cross-link points per unit volume. So low or high cross-link density would imply whether you have low number of cross-link points or high number of cross-link points. I hope you can visualize that whenever you have a high number of cross-link points, you will have a lot of chain which are with very short segments. And this is something which we have discussed in the lecture also. Maybe I'll quickly draw it and show it to you also here. So for example, if we have a cross-link polymer, and these are the cross-link points, what you can see is if the chain is very long. So in this case, you can see that the chain is very long. And if you have, let's say, a high cross-link density, then what will happen is you have too many cross-link points. And so between cross-link points, the length of the chain is very less. And so in one unit volume, you will see a lot more cross-link points. So that's one way of thinking about cross-link points. Radial distribution function, Supratim, I'll explain little later. Let's look at some other questions and then I'll come back to it. As you are rightly saying that you have not seen this, in your AMI syllabus. So it is a subject which is little more for advanced students, but it has become very important these days because experimentally we can in fact capture that radial distribution function. So I will explain it a little later. Let's look at some of the other question. So how is compatibilizer linked with jute or polypropylene or hydrogen bonding? So so you will need a compatibilizer which can interact. So best type of compatibilizer in this case will be one part of the molecule which can have hydrogen bonding so that it can interact with jute, and then other part of the molecule which has hydrocarbon so that it can interact with polypropylene. So you can see that if you have a block type of molecule where there is hydrocarbon kind of a block and another block which has hydrophilic group. So this kind of a polymer can be a very good compatibilizer. Durga Pawan is asking, is there any polymer which has cross-linking structure but recyclable mechanically? So that's in fact mutually exclusive, right? Because whenever you say you have done cross-linking, you have linked all the molecules together, right? So it's an infinite molecular weight. Polymer at one end of the macromolecule is joined because everything is linked in a cross-link network. So therefore, once that shape is fixed, you cannot do recycling because you cannot melt the material. If you de-cross-link, right? If you remove the cross-links by some chemical reaction or by thermal process, then yes. But then you are breaking the cross-link. So a polymer which is cross-linked can be recycled if you are able to break the cross-links. But it's not a very easy process because while you are trying to break the cross-links, some other chains will also break, and in the end you will get a polymer which has low molar mass. Also, in the process, some oxidation and some other reactions may happen which will give you a polymer which is not really what you had started out with. So that's why cross-linking polymers are the most difficult in terms of long-term sustainability and recycling. So are there any other questions based on which then we can proceed further? Depolymerization. So actually, for example, polypropylene, right? If you heat it up, the polypropylene, which is nothing but, and if you heat it, it will end up giving you the propylene back. So this is depolymerization. Basically, the bond which is formed, covalent bond between different propylene molecules, it can break. But this kind of depolymerization doesn't happen for many of the polymers, because when you're trying to do a thermal process, if there is, let's say, small amount of oxygen present, then oxidation may happen. Sometimes pyrolysis reaction may take place. So there are several other possible reactions which take place. And therefore, while you're trying to depolymerize and recover the monomer, you will end up getting several other molecules also. So that's why depolymerization is a desirable, in the sense, it's an ideal world scenario where you say that I take a monomer, form a polymer. Once the application is over, I'll again depolymerize, get the monomer back. But it's not easy, and that's why many of the polymers, depolymerization is still something we are trying to evolve strategies for. Yeah, so Durga Bhavan is asking, for example, polyethylene is cross-linked, and yes, if you de-cross-link it, then you can get polyethylene. But as I mentioned, during the process of de-cross-linking, you may end up reducing the molar mass quite a lot, because there is some other places chain will break. Other issue is you might induce oxygenated groups in the polymer. See, polyethylene works very well in given applications because it's just a hydrocarbon, CH2, 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 CH2. But if parts of the chain gets oxidized and you get some hydroxyl group or some other ether groups and so on, then the properties of that polyethylene will be very different. And if molar mass is not very high, again, properties will be very different. So yes, theoretically, it's possible to get cross-linked polyethylene and get thermoplastic polyethylene, getting a linear and branched polymer. But practically speaking, there are limitations. Ahmad is asking which type of bond form between the polymer and the nanofiller. So that depends on which polymer and which nanofiller are you talking about. Because polymer themselves are, as we have already seen, lots of classes of polymers are there, and then similarly nanofiller also there are different types. So, but generally the bond will be again the type which we have already discussed in terms of some of the interactions between macromolecules. So it could be hydrogen bonding, it could be van der Waals interactions, it could be a reaction also. Sometimes, let's say the nanofiller that you are using might have a hydroxyl group which is attached to the nanofiller. And so macromolecule, if it has a carboxylic acid, then it can react with the hydroxyl which is there on the filler. So both physical and chemical interactions are possible between nanofiller and polymer. But it will depend on what polymer and what nanofiller you are talking about. So Dharmendra is asking whether cross-linked polyethylene is thermoplastic or thermoset. I would ask you to think about it a little bit more, because for thermoplastic, we would need to actually be able to melt the material and reprocess it, or remelt it and then shape it again. Given that it's a cross-linked polyethylene, you won't be able to melt it. And so therefore it's a thermoset material. So this points to the fact that a given macromolecular chemistry need not give you a given type of material. So polyethylene can be thermoplastic if it's linear and branched, but it will become a thermoset material because if it is cross-linked. So generally, Durga Pawan is asking whether LDPE to HDPE conversion is possible. Generally not. See, that's what. So polymerization is carried out, and that is we will later on also in the course we will have how are these industrial polymerizations carried out. So there are several different ways, and once you obtain a polymerization, because the mechanism is fixed, the catalyst is fixed, the reaction conditions are fixed, and so you obtain a polymer, then you can modify the polymer, but you can't make the branches disappeared and make it into HDPE, or HDPE is not branched, so you cannot suddenly add on lots of branches and make it LDPE. So if at all we are interested in making LDPE, we will choose the correct mechanism, the correct reaction conditions, and then get LDPE. If we are interested in HDPE, then we will choose the correct reaction conditions. For example, for HDPE, we may choose Ziegler-Natta or a metallocene catalyst. For LDPE, we may just use free radical polymerization. So mechanism is also different and conditions also may be different. So Supratim is asking whether please discuss about macromolecular nature. So maybe I will just I have already discussed in class several times regarding the molecular conformation. Yes, what happens is in rubbery state, in solution state, and in melt state, polymer is very similar to what is our visualization about a gas or liquid, right? In a gas or liquid, whenever we picture them, what we will say is, there is an atom or molecule and it's randomly moving about. We will never say that it's fixed in space and they are colliding with each other and going about. But in case of solid, we know that atoms and molecules are fixed in space and maybe they will only vibrate around each other. So similarly, if I take now, like these atoms and molecules which are going here and there, if I take a macromolecular chain, the macromolecular chain is moving. So one instant of time, it was like this. The next instant of time, it may become like this. The next instant of time, the same chain may become something like this. So therefore, the macromolecule is changing its conformation because of rotation around CC bond is possible. So which is very similar to, as Supratim is saying, in case of propane or butane or any other molecule. So yes, they are isomers and they are called conformational isomers. And Hemant is asking about degree of polymerization. And degree of polymerization is a measure of how long the polymer chain is, right? As the name suggests, if degree of polymerization is high, more number of monomers have been added on to the polymer chain. And so degree of polymerization is nothing but related directly to the molar mass of the polymer. So for example, if I have one monomer, and then I add, let's say, 4 monomers. Now this is nothing but can be written as M4. So 4 is the degree of polymerization. So basically Mn implies number of repeating units. So I hope that answers your questions. What is the, Shripriya is asking, what is the difference between very low density polyethylene and linear low density polyethylene? So as the name suggests, in case of linear low density polyethylene, what you are doing is you are doing a controlled branching. If you look at historically, LDPE came first. Because free radical polymerization was known, and therefore polyethylene could be produced and using free radical polymerization, and you could get LDPE. And in terms of initial packaging or wire coating and so many applications in which polyethylene was used. Then because of Ziegler-Natta and other catalytic systems, we could get control on getting a linear polymer. And that's when HDPE came about. Then scientists thought that if you can control the branching well, you may be able to get properties which are superior in terms of film making. Because HDPE is not very good for film making. Its properties are much better than LDPE in terms of mechanical strength and all that, but you can't really make it into a film because it's a linear molecule. And we will see this during the course that whenever we have branched molecules, its extensional stretching behavior is much better. So now, but if you have too much branching, then properties again go down because it cannot be crystallized and so on. So linear low density polyethylene is a good combination of HDPE, which is largely linear, and LDPE, which is heavily branched. Yes, ultra high molecular weight polyethylene by Ziegler-Natta or metallocene catalysts are possible. And Durga Pawan is asking, sustainability of material is studied by life cycle analysis. Yeah. So we don't, in this course, we will not discuss life cycle analysis. However, sometimes I will give you numbers which are based on studies of life cycle analysis cost to make the point. But we will not really cover life cycle analysis in this course. Yeah, so maybe if there is a lot of interest, then maybe we can have some interest later towards the course. I can discuss life cycle because Supratim is also asking. But see, life cycle analysis is really outside the scope of this course. This course is about polymers. In analyzing the sustainability, life cycle cost is one important parameter. So one important method. And so right now in this course, what we will do is we will assume somebody else has estimated life cycle cost, and we will use those numbers to try to get an idea about why or how polymers can be made more sustainable. But in our course, we will not be really looking at how to estimate the life cycle cost, because it's a procedure in itself. So I can see Lokesh is asking, but the question is not complete. Maybe I'll let. So Manikandan is asking about glass transition, and it's a very important property. And the third week and fourth week, we will have a lot of discussion related to glass transition. So those of you who have done thermodynamics, quite often you will think that entropy is a very difficult concept because it's not possible to define it one single way, so glass transition also is a concept which is similar in the sense that it is depends on what is our interest. However, all of you are engineers and scientists, and if I ask you the question, what is force or what is mass? So all of you will say that we understand that very well. But if I ask you to define it in one sentence, I'm sure all of you will come up with slightly different definitions, and then sometimes you will say force is related to this. You will talk about actions due to force. Sometimes you will talk consequences of force. Sometimes you will say how you can feel the force. But somehow we never ask this question. Tell me what is exactly force. We somehow know, since school we have learnt about it, we somehow know what is force. But same thing is true about each of these concepts: mass, force, entropy, glass transition. All of them are complicated concepts. It's just that this is the first time you'll be exposed to glass transition, so you may feel initially that it seems to be a tough concept. But we'll spend at least 2-3 lectures exclusively on glass transition itself, and we'll take several examples to talk about glass transition. In the end, it's related. Glass transition is related to what's called a segment of a polymer chain. We generally talk macromolecule is very long. I don't know if you can visualize if polymer is, let's say, as the diameter is like my hand, what is its length? And if you think about it, if diameter is like this, which is about, let's say, 5 centimeters, 4 centimeters, then its length is going to be in kilometers. So it's an extremely long object. But the bond angle, rotation, and all of that is happening at a very small scale. So in macromolecule, you have flexibility and motion related to the whole macromolecule or also related to part of it. And the part of it is called a segment. So at glass transition, segment stops moving. Above glass transition, segment can move. Below glass transition, segment stops moving. So we'll discuss this more. So right now, Manikandan, I'll just say this. You'll have to wait and look at the next set of lectures where we'll discuss glass transition. So vulcanization also we will discuss, Supratim, but vulcanization is a cross-linking process where, for example, historically sulfur vulcanization of natural rubber. So sulfur cross-links by covalently bonding to polyisoprene chains. So it's not that it changes the branching, but it cross-links the polymer system. What do you mean, Durga Pavan, by closures of plastic containers? You mean the cover caps? You will have to clarify. Lokesh is asking a question related to biodegradable polymer, and we have lectures associated with biodegradable polymers and what is biodegradability. For example, polylactic acid is an example of a biodegradable polymer, Lokesh, and of course, we know that many of the natural polymers are biodegradable. For example, pectin is a natural polymer, starch is a natural polymer, and they are biodegradable. So we can have various examples of biodegradable polymers, and we have 3 lectures on this topic as well. Lokesh, your earlier question related to PVC was not complete. It just says PVC are prepared by. So I don't know. You can maybe retype the question in case you are still interested. When compared to container body, I don't see why caps will have to have more or less properties. In the end, let's say if you make a PET bottle, if let's say for soda, let's say carbon dioxide is inside and we don't want it to escape, then whether it's cap or bottle, both of them should not allow carbon dioxide to go out. So in general, the barrier properties will both be required. However, while we remove the cap and while we put the cap, the mechanical load that we are putting is different, and therefore their mechanical properties can be different. How to recycle PVC? Okay, so that's a topic which today I will not discuss, PVC recycling, but in later on again we will see if there is a lot more interest than one particular polymer and its recycling strategy we can discuss. Yeah, tacticity is basically related to the group, side group on the polymer and how it's located in 3-dimensional space. So I think best thing to do about tacticity is to actually go to YouTube and search for videos related to tacticity and then look at it. Because right now, for example, I can just say that, you can just have, let's say, a polymer with this group R, right? But if you look at this kind of a group, what happens is this is in 3 dimensions. Three dimensions, if you look at the polymer let's say the backbone or the CC bond can go like this. So there are C, 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 and then on this you have hydrogen, and then on this you have hydrogen. And so if I travel along this way, what is the location of the 2 hydrogens and what is the location of R on one side and hydrogen? If all of these are identical, if all of these, so for example, if this R is also H, then it doesn't matter, right? If I travel along this, whether it comes to my left or right or how it's there, all of them are hydrogen, and so location doesn't matter. But out of the 4, if one is not hydrogen, so for example, for PVC, this will be chlorine. So you can have either chlorine for PVC or CH3 for polypropylene, or you can have it as the benzyl group for polystyrene, then in all of these cases, tacticity is possible because you are looking at what's the location of this group when I am traveling along the polymer chain. But I think much visual better thing of this is related to the rotation of these bonds, and maybe I'll search some topic and then I'll share it on the forum so that you can see, and that will be much better explanation. So Kushi, I hope that answers your question for now. But as I said, visualization is much better if we just look at one of the animations. So I'll share one of the animations with you. Okay, Supratim is asking a question related to queries. So no, WhatsApp queries are not fine because there is no way I can address. And first of all, I'm not very active on WhatsApp. And secondly, forum is the best place to ask queries. Because what happens is whatever query you ask, it might help the others. And what will be really nice is if some of you can also start answering each other's queries. Because if you can answer somebody else's queries, that means you have learned the subject very well. And sometimes if I answer a query, there can be a follow-up question by a third person. So that kind of a discussion will be very interesting as opposed to sort of always only listening to lectures. So that's why, for example, in the first week of the class, I sent you, all of you, an email saying, you know, go and look what mucin is. I don't know if any of you looked at what is mucin. Did you get this email which I sent about, you know, look at mucin? You can just say yes or no on the chat. Just to let me know whether you saw the email in which I said, you know, go and look what mucin is and think about its molecular structure and think about its molar mass and where it is there in the body and so on. So did you get that email? Do any of you remember seeing that email? I'll just wait half a minute just to see your responses, because there is a small delay after I say it and the video has to get beamed down. Okay, so Shakir is saying that actually you didn't see it. So I think you probably get a lot of emails from NPTEL, and maybe there is a tendency of yours not to read each and every email, but therefore, what I suggest is you please log on to the forum and look at it. Because forum is where the discussion will be very useful. And in fact, like what Kushi asked related to, you know, the tacticity, or question related to PVC recycling. So all of that we can discuss in the forum. So as of course, any interaction will not be complete without asking questions related to exam and what type, and that's what Supratim has done. So no, questions will not be only MCQ type. There will be numericals also. There will be some derivations also, which can be converted to MCQ type or the numerical type. You will see that. Okay, so yeah, so actually I'm surprised. So I'll check anyway. Most of you are saying that the email was not received. So there are two emails that I sent. In fact, one email I sent this week, which was related to molar mass distribution. I saw that one of you had also asked, you know, explain a little bit about number average molar mass. So each of this is related to different weight that we give in terms of finding out the average. So if you look at, let's say, a set of polymers, and Maybe I can give you an example first, which is, let's say, I have a few polymers in a mixture. And so let's say there is one polymer, second polymer, third polymer, fourth polymer. So I have all these different sets of polymers, right? So there is molar mass is different for each of them. And so what if I want to characterize the sample, then average molar mass is required. Now, how do I calculate the average molar mass? So there are multiple ways in which we can do this. So one thing I can do is I can just count the number of molecules with a given molar mass. Right, so let's say the number of repeating units. This case is I'll just start giving some number. Let's say number of repeating units here is 500. Then it's 300. Then this is, let's say, 700. Then this is 200, and then this is 550. So all the different polymers have different number of repeating units or degree of polymerization. So clearly, if I give you a mixture like this, you can see 500, 300, 700, 200, 550. So you will immediately say that, okay, the number average will be somewhere around maybe 400 or so. But if you, but there are multiple ways of calculating this average. One, you can say that I will find the number of molecules which have this repeating units. So that's one way of doing it. So based on number of molecules with n units. This is one way. This is mn bar. The other way is weight of molecules with n units. Because in one case we take only the number of molecules which have n units. In the other case, we say we count those molecules and then we multiply them by their molar mass so that we get weight of those molecules. So that's why these two are two different molar masses. Shakir, your question related to photons, maybe we'll discuss later. Right now, I don't know why it's relevant to whatever discussion we have. Maybe if you explain as to what is the relevance of some of what we are discussing, then maybe I will try to answer that. Yeah, so Supratim, what I would suggest is on forum, you please post what exactly is the problem, which problem are you finding it difficult, and then I can start solving on forum itself. What I can do is on forum, I can include some small audio file or some small sheet in which I have solved something, and I can introduce that so that all of you can go through it. So it looks like, okay, this was a good starting point for me to start interacting with you. But I hope that many of you will continue this by looking at the forum a lot more closely and watching the videos and then posting questions related to those videos on the forum. Because I look at forum almost every day, and if there is a query there, I will try to answer it immediately. So you please spread the word around also, and I'll check also as to why whatever emails that I sent was not received. Because, for example, Supratim is saying that checks the email quite thoroughly. So I'll just check that. So are there any other questions? So it's just the first week. So and second week videos you have started watching. This is an introductory course on polymer, and lots of exciting topics related to polymers we'll be discussing. Generally, we will, Supratim is asking whether when will we have next session like this. I plan to have at least once a month or maybe twice a month. So I will see. What I need is also some sort of interest, and what are your range of interests on the forum. So then based on the forum response, then I can decide, based on the forum, then I'll say that, okay, these 4 topics, lot of interest is there, so I must do a live session. So then I will do a live session. So therefore, the number of live sessions will depend on how effectively we are interacting on the forum. So Dharmendra is asking whether I will discuss characterization techniques of polymers. For example, so IR, there is a small discussion I have in one of the lectures. UV visible or SEM-TEM, no, not really. We are not really going to discuss those characterization techniques. Any introductory course on material science will discuss that, because see, many of these techniques are valid for all types of materials. So therefore, for our course purposes, we sometimes will see the response. So for example, in natural fibers, I showed some SEM picture of the fibers or particles. So that kind of results we will see, but basics of what those microscopic techniques are, you will have to look at one of the material science courses. So Dharmendra, I won't be discussing characterization techniques, but we will discuss several other characterization techniques which are very crucial to polymers. For example, dynamic mechanical analysis or rheology or differential scanning colorimetry. So these techniques are used a lot more for polymers, and we will discuss them in more detail. Even let's say impact testing of polymers. So those things we will have much more emphasis in this course. So Abbas is asking whether in a copolymer is the degree of polymerization the number of monomeric units or the number of repeating units. So I don't really understand the question. In fact, you had posted also prior to the class itself in the sheet. Abbas, you'll have to clarify a little bit because first of all, maybe you give an example as to what do you mean by copolymer, or what do you understand by copolymer? It's a copolymer of what? So by the way, in the 4th week, we have lectures which will be on copolymers and also different types of copolymers. So the lectures will be there, but before I answer your question, Abbas, I need to know what do you mean by copolymer, and can you give an example of copolymer? And what do you mean by monomeric units of that copolymer, and what do you mean by repeating units? For example, polyester is not a copolymer. Polyester is polymerization of a diol with diacid. So monomers, if you see, there is a diol or there is a diacid. But polyester is not a copolymer because diol by itself cannot form a polymer, or diacid by itself cannot form a polymer. Acid needs to react with alcohol to form the ester bond, and only then you get polyester. So that's why in case of polyester, we have the repeating unit, which is different compared to the 2 monomers. So I'm not sure if Abbas, this point is clear. So I'll wait before answering your question. So nylon 6 is not a copolymer. Nylon 6,6 is not a copolymer. It's a condensation polymer which is prepared by reacting 2 monomers, because this is a reaction of step addition where the monomers react with each other and slowly build the polymer. And monomer by itself cannot give. So amine by itself cannot give you a polyamine, or a diol itself cannot give you. So therefore, what you See, these are all examples of homopolymer. We say something is copolymer when the two monomers that you are adding can themselves form a polymer. So ethylene, polyethylene, propylene, polypropylene. So if you make a copolymer of ethylene and propylene together, it's called ethylene propylene copolymer. So nylon 6,6 is a homopolymer, and repeating unit is the weight describing thing, because monomer identities are lost. Generally, monomers react a molecule like water or ammonia or some other condensation product is there. So therefore, finally, what's there in the polymer is really a repeating unit. So Abbas, therefore, in nylon 6,6 case, it's the repeating unit weight which is important. But of course, it's related to the monomer weights. So the two monomers weight you have to add, and then you have to subtract the weight of whatever is the molecule formed, like water, condensation product, and then you get the repeating unit molar mass. So therefore, they are all related to each other. Tire industries use a mixture of rubbers. So it's not just one single rubber. Natural rubber is used in parts. SBR, styrene butadiene rubber is also used. It has nylon threads. So it's a combination of several types of polymers, and in fact non-polymeric materials also. For example, carbon black is a very important component as a filler. There are metal threads also. So therefore, it's a combination of several materials. Yeah, can we find molecular weight of thermoset? No, it doesn't make sense, right, Dharmendra? Because in case of thermoset, the molecule is just one infinite molecule, because it's joined with crosslinks from one end to the other end. So if I make this whole big object with thermoset, what will happen is this part of the molecule is connected to this other part. So it's infinite molar mass. This whole block will be one molecule only. But in case of thermoset, therefore, what's interesting to know is what is the polymer distance between, or the polymer length between two cross-linking points. So therefore, crosslink density, which means number of crosslink points per unit volume, and the length of the polymer chain between two crosslinks are the parameters that you can find out. So you can find out crosslink density, or you can find out crosslink chain length distribution, and those are more appropriate compared to molar mass. Durgapan, you're asking, is this information allowed, sir? So I don't understand. You have maybe said something about another course. Yeah, please. We see in all of this, there are very different resources, and all of them are very useful. So try to use as many resources as possible in terms of learning the course. Okay, we are nearing towards the 1 hour mark. So if there are questions, you can ask them. Otherwise, we can start winding up. I hope that what I have also tried to do during the overall course is show some of the GATE questions. And those of you who are preparing for GATE, or those of you who are anyway preparing for competitive exams, will find it useful. So you will find that GATE questions are there in lectures also. They will be there in assignments also. And in fact, in forum, what I had posted was one GATE question from 2010. There was one question which was asked on the sheet. I don't know whether the person has joined or not, whether can we make polyethylene to be electroactive? And I got reminded of that question because Anirudh Krishna is also asking, is it possible to incorporate ionic polymers and biopolymers for technical textile applications? which would in turn conduct electricity. Yeah, so that is certainly possible. So what you can, if let's say from a textile application point of view, you need electricity conduction, but at the same time you don't want to use or you want to use a sustainable polymer, let's say similar to a biopolymer, then you can incorporate ionic groups. Many biopolymers have ionic groups, right? DNA, for example, is ionic. Proteins have ionic groups. Polysaccharides will also have some ionic groups. So many of the polymers which are there in the biological world have ionic groups. So it's certainly possible to incorporate the ionic groups in biopolymers. No, Supratim, that's very low density polyethylene. So you can look up. I will leave you that as an exercise as to what. Because we have described in class low density, linear low density, high density. There is also ultra high molecular weight polyethylene, UHMWPE, and that's used for fibers. In fact, its mechanical properties are as good as many other metals and those kind of systems. Yes, you can ask also any doubts that you have related to, if there are some questions which are there from other exams which you have some doubts, but only thing is you should ask it during that week when we are discussing that concept. So for example, if the question is related to glass transition, then you can ask it during that time, or what you can do is you can ask it now, but I will keep it aside and I'll answer it whenever we are discussing it. Right now, for example, I didn't really answer the question related to glass transition because that discussion is yet to happen in the course. So anyway, I'll go through the chat box again and then I will try to see what will be the different types of questions that have to be answered, and I'll answer those. So I will just, given that there are only 2 minutes remaining, I just wanted to make some remarks regarding, polymers, and they are used very widely. And so in some sense, they are smart materials in the sense that, they give us the performance that we want. And we use them in plastic objects, films, pipes, aerospace, automotive, you name it, they are used. But futuristically, can we get smarter polymers? And that's really the R&D topic as well as innovation topic for all of us to think of. And what is meant by this smarter could be in terms of properties, it could be in terms of sustainability, it could be in terms of responding like a sensor or a actuator, or it could be a conducting material. So smarter can mean variety of different things. And so a lot of polymer science and engineering now is dedicated towards going from polymers which we already know are used quite a lot to a set of polymers and use them in applications which are much wider compared to whatever we are using so far. So with those, maybe in one of the other live sessions, I'll give you some examples of these smarter polymers from an R&D point of view. Because during the course, we are discussing far more basic concepts, but during one of the live sessions, we can discuss a little bit more about innovation and future topics related to polymers. So with this, we will stop now. I thank you all for joining and making it a very lively session by asking lots of questions. Some of the questions I have not answered, which I will answer on the forum. Please find out how to join the forum and keep track of it. because a lot of our discussions will hopefully happen on the forum. So with this, again, have a good evening and good night. And I will see you again live sometime after maybe 2. I will also log out now. Okay.